So now let's start getting closer to a more practical circuit. I'm going to just get this out of the way. I need just a little extra room, so just remember, I'll just write it over here. Our HFE equals 10. Don't need that anymore. And I'm going to add a little more to the circuit. I'm going to put another resistor here. This is outside of the transistor. And we're going to go to a voltage source over here. And let's just make that 10 volts. And so here is the collector of the transistor right here. Here is the emitter. Of course, the emitter is also over here. Just emphasizing these are separate circuits, even though they will be connected. They operate completely independently of each other. And I'm not going to put any more over here. We'll just say there's certain base currents. That means there's some circuitry out here causing that. We're not going to worry about that. We just want to know what's going on over here. So there's 10 volts. Let's make this a 1K resistor. Let's clean this up a little bit here. That's not going to be like that anymore. Our collector current is going to come this way. So this is outside the transistor. This is inside the transistor. So far we haven't changed much, but we are interested in what happens at the collector because that's going to be our output voltage of our common emitter amplifier. So we have a voltage between the collector and the emitter that we're very interested in. So the voltage between the collector and the emitter, called VCE, voltage between the collector and the emitter. So that's this voltage here that we want to monitor as we change our base current. So let's get that out of the way. I'm going to draw a small graph. I'll expand this at another time, but let's just draw it small right now. Here's our voltages. There's our 10 volts. There's 0 volts, 5 volts, and different currents. Let's say this is going to be 5 milliamps, 10 milliamps, and 0. So we have our collector current over here and our VCE down here. And let's look at our voltage compared to our current as we go through different base currents. So let's start with something simple. Let's put 100 microamps into the base. What's causing that? I don't care. There's some circuitry causing that, but I have 100 microamps in the base. So what's the little green man do? He says, 100 microamps, have to multiply that by 10. So what's 10 times 100 microamps? We're going to have a collector current over here, I sub C, of 1,000 microamps. And of course, how else can we express that? 1 milliamp. So there's our 1 milliamp of base current. When we have 100 microamps going in there, what's going to happen to our voltages here? Well, we have 1 milliamp going through 1K of resistance, starting with 10 volts over here. So 1 milliamp through 1K, how much voltage will develop across that? Remember, whenever you have current going through a resistor, you're going to get a voltage differential across it. And the highest voltage will be where conventional current enters the resistor. And the lower voltage will be where it exits. I'll label those as plus and minus. So how much is that voltage difference going to be? Well, Ohm's law tells us. We simply multiply those together, and I use some easy numbers. If we multiply milliamps times kilo ohms, what do we get? Whole volts. So with 1 milliamp going through 1K, we're going to have between this point here and there across the resistor 1 volt. And it's going to be highest there, lowest there. So what's the voltage right here? It's going to be the same as the battery voltage. There's nothing between here and the battery except a little bit of internal resistance in the battery. So basically this voltage along this wire is going to be our battery voltage, which is going to be plus 10 volts. So if we have plus 10 volts and this voltage must be 1 volt lower, what do we have left? Plus 9 volts. So under this condition, with 100 microamps and an HFE of 10, we have 1 milliamp going into the collector. Why? Because the little green man has adjusted this resistor until we have 1 milliamp going into the collector. That gives us 1 milliamp through 1K. which means we have 1 volt from here to here across that 1K resistor, leaving us with 9 volts here. Does that add up? Let's see, Kirchhoff's voltage law says that this voltage plus that voltage must equal that voltage. 1 plus 9 equals 10. Everything works. So under this condition, with 100 milliamps in the base, we have, what's our current? It's going to be 1 milliamp. So it's going to be somewhere along here. Let's put a little tick mark right here for 1 milliamp. And we're going to have 9 volts. That's going to be somewhere around here. Let's put a tick mark there for 9 volts. So our voltage and current come together right there. 9 volts, 1 milliamp, right at that point there. Okay, let's go ahead and increase this to 500 microamps. What's that going to do? Little green man sees 500 microamps, HFE of 10, so he's going to lower his resistance until he sees 5 milliamps. 5 milliamps is 10 times 500 microamps. Let's see what else changes here. Well, that's going to change. That's going to change. So we have 5 milliamps going through 1K. How much voltage are we dropping across this 1K resistor? Well, if we multiply milliamps times kilo ohms, we get whole volts. So 5 times 1 is going to be 5 volts. We start at 10 volts. We lose 5. We have 5 volts left over. So our VCE is going to be 5 volts right there. Our collector current is 5 milliamps. So where do those come together? Right about there. Now let's go up to 1,000 microamps. So 1,000 microamps is equal to 1 milliamp. Little green man sees that and says, oh, I have to multiply that by 10, so he's going to drop his resistance until he sees how much? 10 milliamps flowing into the resistor. So adjust the resistance down until he sees 10 milliamps. What's going to happen here? Those are going to have changed, of course. So 10 milliamps going through a 1K resistor, that's going to give us 10 volts across there, so we lose 10 volts. What do we have left over? Well, this voltage and that voltage must add up to that voltage. So if this is 10 volts, we can't have anything left over, so this is going to be 0 volts. So let's look at our voltage. There's 0 volts. How much current? 10 milliamps. That's going to put us right there on the edge. Notice we have a nice straight line representing the voltage and current going through this transistor under these conditions. Interesting thing is that this slope of this line is directly proportional to that resistor. So let's see what happens if we change that to 500 ohms. Little green man's going to do his job the same way. Let's get rid of these numbers here. Let's put our current back. Okay, let's go back to our 100 microamps. So 100 microamps. Little green man is going to adjust his resistance until he sees 1 milliamp. Let's draw it at the meter here. 1 milliamp. Should have done that earlier, but you got the picture. So he sees 1 milliamp. So 1 milliamp going through 500 ohms, well, that's going to be half the voltage we had with 1 milliamp going through 1,000 ohms. So 1 milliamp times half of a K is going to be 0.5 volts across there, leaving us with 9.5 volts from the collector to the emitter. So at 1 milliamp, we're going to have 9.5 volts from the collector to the emitter, so it's going to put us somewhere like right about there-ish. Now let's move this up to 500 microamps. That's going to increase this to 5 milliamps. He's going to decrease his resistance till he sees 5 milliamps. What's that going to do to our voltages? Well, when we had the 1,000 ohm resistor here, we lost 5 volts, but with half the resistance, we lose half the voltage. So we're going to lose 2.5 volts. What's that going to leave us here? 7.5 volts. So it's going to be plus 7.5. 10 minus 2.5 leaves us with 7.5. So somewhere like right about here, 7.5 volts. What's the current? 5 milliamps. So it looks like we're going to be right about there-ish. Maybe a little Higher, there we go. Okay, let's go back up all the way to 1,000 microamps, which is really 1 milliamp. That's going to give us 10 milliamps through the circuit. 10 milliamps through 500 ohms is going to give us a voltage of, well, we had 10 volts before, but now we're going to only have 5 volts. So 10 milliamps through 500 ohms gives us 5 volts across the resistor. We start with 10, we lose 5, so we have plus 5 volts here. And so what do we have? We have 10 milliamps way up here, 5 volts there, so we're going to end up with right about there. So now our slope, if I can draw a straight line here, is steeper. And it's going to go on up, and it won't reach 0 volts until we get all the way up to 20 milliamps. So I only drew up to 10 milliamps here. We have to go up all the way to 20 milliamps to lose all of our voltage if we have a 500 ohm resistor. So notice that this slope got steeper when the resistor got smaller. If we make the resistor bigger, the slope will get lower. So I just want to redraw this real quickly and emphasize what I just said. This is going to be a practical schematic circuit here. There is our NPN transistor. We know it's an NPN because the emitter arrow is not pointing in, not pointing in, NPN. So that's how we can remember that's an NPN transistor. We have a base circuit going on over here. I'm going to go ahead and draw my resistor and my voltage here. Common emitter circuit. We can vary that. Collector resistor here. Supply voltage over here. And there is our collector voltage. So collector, base, emitter. Let's make this 10 volts. Make this 1K again. So here's our practical circuit. There's our output there. We're interested in the voltage at the collector. What do we call that voltage? Voltage from the collector to the emitter. So that's VCE. And so as we get a little bit of base current in here, what happens? We get a lot of collector current. We have current going through this resistor, so we get voltage across it, and whatever voltage is across here, we lose starting at plus 10 volts. If I have 1 milliamp, I'm going to lose 1 volt. So I start with 10, I lose 1, I have 9 left over. What happens if I increase this current? So now I have 2 milliamps across 1K, I'm going to lose 2 volts. Start with 10, lose 2, I have 8 left over, so my current went up. My voltage at the collector, current gets higher, the voltage at the collector goes lower. My current goes lower, the voltage at the collector goes higher. So as this collector current increases, my collector voltage goes down. As this collector decreases, my collector voltage goes up. So I just want to emphasize that, and we already went through the exercise of what specific base current gives us a specific collector current and specific voltages. Okay, so there's the basic idea of how the transistor works in this configuration, but I need to look at the extremes now. So let's go back to our little green man model. And let's see, there's our current meter, our resistor, and our collector resistor to our battery. And it keeps coming to mind, I might as well say it while I'm thinking about it. There's a name for this voltage. It's called VCC. Why is it called that? Don't really know. Here's our collector, here's our emitter, there's our base. So it's close to the collector, but I have searched and searched and I cannot find a good authoritative reference as to why that's called VCC. I did look it up on ChatGPT and it gave me this scientific sounding answer that I know is wrong, so I'm not even going to repeat it. But what I can tell you is if we have a field effect transistor where we have a drain, a source, and a gate instead of a collector, emitter, and base, and that voltage with a field effect transistor is called VEF. VDD. Close to the drain. If we have a tube circuit, there's our grid, there's our plate, there is our anode. So plate, grid, anode, and that voltage is called VPP. So you figure it out. Exactly why they came up with that notation is lost in history. I cannot find an authoritative source that says what it is. But notice that if it's a collector, it's VCC. If it's a drain, it's VDD. And if it's a plate, it's VPP. Go with that as you will. Okay, so there's our circuit ready to go again. Let's put our variable resistor here and our little green man doing his job, controlling the resistor, watching the current meters. And we'll put our HFE over here. And now we're going to look at what happens when we go to the extremes. First of all, let's go to our maximum base current. We're going to use the same circuits. Let's make this 1K and make this 10 volts. And let's make our base current 1,000 microamps, which of course is the same as 1 milliamp. So what's going to happen? HFE of 10, he's going to lower his resistance until he sees 10 milliamps. So now we have 10 milliamps flowing through that resistor. And what's going to happen? 10 milliamps through 1K. We're going to lose 10 volts plus 10 up there, 10 volt battery. Start with 10, we're going to lose 10 and have 0 volts here. Okay, let's take a look at what happens if we increase our base current. Let's go up to 1100 microamps, which is going to be the same as 1.1 milliamps. He's going to see he needs an HFE of 10, so he's going to do what? He's going to lower his resistance until he sees how much? Till he sees 11 milliamps. So here he goes, lowers his resist. Uh-oh. Come to think of it, to get that 10 milliamps, he had to lower that all the way down to 0 ohms. So what do we have here? We have 10 milliamps going through 1K, we get 10 volts. This voltage plus that voltage must add up to that voltage. So that means this voltage must be 0 volts. And if we have 10 milliamps going through a resistor and get no voltage, that must be 0 ohms. So he's already cranked that down to 0 ohms. And he says, hey boss, I can't get this any lower. So are we going to get that 11 milliamps? No, we're stuck at 0 ohms there. He says, sorry boss, I can't give you lower than 0 ohms. You can increase this to 5,000 milliamps if you want to. I can't crank that any lower. So the best you're going to get is going to be 10 milliamps and 0 volts here. So we've reached a condition we call saturation. And what is saturation? Saturation is when increasing the input no longer changes the output. So as we increased our input, the output kept getting lower and lower and lower, can't go below 0. So now we can increase the input till the cows come home, but we're not going to change the output. So we've reached the condition of saturation. Now what's going to happen if we go to the other extreme? No base current. It's a 0 base current, HFE of 10. 10 times nothing is nothing. So he's going to crank his resistances up as high as he will go. He's going to try to go all the way to infinite resistance. And wants to see 0 milliamps here. No current here. So no voltage, no nothing. So what's going to happen? Well, I should say there's something, because what's happening here? We have 0 milliamps. So 0 milliamps going through 10K. How much voltage are we going to develop across this resistor? None. No voltage. 1,000 times nothing equals nothing. And so if this voltage and this voltage must add up to 10, that means we have our full 10 volts over here. So our VCE and so can we make the make this go any lower? Not really. We've reached the bottom there. But in reality, with 0 amps going in here, remember that the transistor did have a small current. Depending on the transistor, it's going to be a few nanoamps to a few microamps, but we are going to get some current. So in reality, let's get some of this out of the way here, we have something that looks like this. He's got a little resistor in parallel. Remember that resistor in the hybrid model that was in parallel with the current meter? Well, I've got the current meter out of there here because what current goes through here also goes through there. But here's our HOE, or 1 over HOE. And that's going to affect our minimum current because even though he has this at infinite ohms, there's still a little bit of resistance here. So we will have a little bit of current. And regardless of what the HOE is, we're still going to have some current flowing through here because of the nature of a transistor. Occasionally, charge carriers appear from thermal energy and they flow and disappear, and we get tiny bits of current even if we have no base current whatsoever. And that's going to be our, remember this, ICBO. When we reach a condition where increasing the input no longer changes the output, we call that saturation. What do we call it when decreasing the input no longer causes a change? We call that cutoff. There's a minimum current called the cutoff current, more often called ICBO. And so there's going to be some minimum base current that we go below that, it no longer changes it, and we are now in the condition of cutoff. So saturation is when increasing the base current no longer causes a change in the output. Cutoff is when decreasing the base current no longer causes a change in the output. Now that I've talked about that, I do need to go back to the saturation because I showed saturation as when we had the maximum conditions. Let's get rid of our clutter here. So let's increase this back up to 1,000 microamps. He's going to see HFE of 1,000 microamps. He's going to drop his resistance all the way down to 0 ohms, trying to get maximum current. So we should get 10 milliamps, and we should drop 10 volts here, leaving us with 0 volts. VCE equals 0, right? Well, there's a slight problem here too. And where am I going to draw this resistor? I need room for a resistor. I'm just going to draw a little tiny one right up here. This is something you don't see in any of the engineering models, but it must exist. There's a little bit of resistance there, and so I go down to 0 ohms, I've still got some resistance, so I cannot get that all the way down to 0. And so, since I have a little bit of resistance, I've got current going through that resistor, don't I? If I have current going through that resistor, I'm going to get some voltage. And so, when we are in saturation, we do get a small amount of voltage. It might be from 0.3 to 1.2 volts. I'm just trying to think off the top of my head. It seems for some reason 0.4 volts sticks in my head, so I'll just put that here. But this is not typical. It's just somewhere in the middle, a good voltage for that minimum voltage. So that's the voltage developed across that little resistor because the little green man cannot get to 0 ohms. So there's a name for that voltage. What's it happening at? It's happening at saturation. So we have a voltage from the collector to the emitter when it's saturated. And so that's what we have right there. That little resistor causes that saturation voltage. So what's going to happen here? Well, it's going to make some changes here. So we have minimum voltage here, VCE sat. Absolute minimum voltage from the collector to the emitter is 0.4 volts. So what's the maximum voltage going to be across here? Remember, that voltage plus that voltage must equal 10. So 9.6 volts is the maximum voltage we can get across this resistor because we can't go below that voltage. Does this add up? 9.6 plus 0.4 equals 10. Adds up. So the maximum current we're going to actually get is going to be 9.6 milliamps. Let's draw it down here. 9.6 milliamps. So all things being ideal, if I have 1 milliamp in the base in an HFE of 10, my resistance should go down to 0. I should get 10 milliamps through this resistor. I should lose 10 volts across it, have 0 volts here. I'm in saturation. but in reality, I can't quite get there. So I do reach a point somewhere before I reach that 1000 milliamps where going higher is not going to have an effect on the output. And of course, that's the saturation point. So let's do a quick review of all the stuff we just said. Here is our circuit again. And there's some base circuit out there, NPN transistor, 1K, 10 volts. So as I get a little bit of current through here, what do I get? A lot of current through there. As I increase my current across here, I get more voltage across it. So therefore I drop more voltage. So more current through that resistor means a lower voltage at the collector. If I go below a certain base current, I get to a point where I get a minimum amount of collector current called ICBO. So I go below a certain base current, I no longer change the collector. I get the lowest possible collector current, known as ICBO. That condition is called cutoff. And if I increase my base current, I get to a point where increasing it no longer changes the output, and that's going to be a condition called saturation. When I reach that condition, I'm going to have my maximum current, but I have a minimum voltage from my collector to the emitter called VCE sat. And I'll throw in my 0.4 volts there. Again, that's my absolute minimum voltage there, which determines my maximum current here. And so once I reach that saturation, increasing my base current will no longer change the circuit, and that's my minimum. So I have a minimum current called our cutoff current. We have a maximum current called the saturation current. That saturation current is determined by external sources. We calculated that a moment ago. But when we get to that maximum current, that means we have a certain minimum voltage here called the VCE sat. So that is how our transistor works in a more practical look.